All right, let's get started. Thank you for joining me this afternoon. My name is Arunachalam Thiraviam, and I'm a simulation product specialist with GoEnginneer. Today, I'm going to go over some new capabilities in 2018 called Free Surface Flow in SOLIDWORKS Flow Simulation. I'd just like to tell you that your mics have been muted, so if you have any question, please, write it down in the chat in the GoToWebinar application, and I'll be able to get to those questions towards the end of this session. Now let's get started. As I mentioned, I'd like to talk about the free surface flow concept in flow simulation that was introduced in 2018. Now, what the free surface flow entails is your ability to simulate the flow of two immiscible fluids. Now, set of immiscible fluids is essentially two fluids that cannot mix and form a homogeneous mixture. So these two fluids would be separated by something called a free surface. For instance, if you take this aquarium, this little orange line indicates the separation between the air and the water. There's no mixing, they're separate phases. Now, on the contrary, an example of a miscible fluid would be, say water and alcohol or water and any kind of organic fluid. Now, this is a very popular technique in commercial CFD where people would like to simulate the effects of water in an open container where, there is the effects of air on the water. So typically, the ability to simulate air and water in the same domain or any two fluids that don't mix give you a lot of insights into the behavior of the fluids, without simulating any mixing. Now, the approach that we essentially use here is called the volumes of fluid approach. There are several approaches that are built into several CFD tools, and the volume of fluids approach is the most popular one. Now, this essentially involves solving a set of momentum equations as usual. And what it does in addition to this is to track the volume fractions of the different fluids in your domain. So if you take a fluid, it can have a volume fraction that varies between 0 and 1. Now, if you take a cell of the mesh, now there'll be many fluids within that cell that essentially have a volume fraction range from 0 to 1. So the sum of all the fluids within a cell, or the volume fraction sum, should be 1, should be unity. Now, the free surface is maintained where the volume fraction of one fluid transitions from 0 to 1. So essentially, you're able to simulate multiple fluids within the same cell. In SolidWorks Flow Simulation, for now, we are able to simulate two fluids within the same cell. And I'd like to show you some common applications of this approach. Yep, as I mentioned, the most common application with this kind of free surface flow is the inertial effects of fluid flow. For instance, let's take an automobile like a motorcycle or a car with a fuel tank that's trying to execute a corner. Due to the inertial effects on the fuel tank, it essentially causes the fuel to slosh around. Now, it's very important in the field of structural analysis and vibration analysis to understand the various forces experienced by the tank due to the sloshing, and we are actually able to generate those results. Now, continuous flows is another application. If you can think of a spout, a water spout, so you want to see how much pressure translates to what distance the water can travel through the air. Now, another application is how you can fill or evacuate a tank. Now, besides this, external large-scale flows involves simulating the wave resistance offered by water on the hull of a ship or a boat or a submarine, anything that essentially goes on water. Now, there have been a lot of applications that have been floating around in the SolidWorks channel, and here are a few applications that I thought I'd quickly throw on the screen. So this should give you an idea of the sloshing effects that I was talking about. Later in the webinar, I have an example that's set up that shows you the sloshing effect. Now, the fountain here, this is the this essentially shows you how much pressure translates to the height of water traveled. So different pressures, give you different distances, and you're able to see once the water hits the ground what the spread is as well. Now, the wave resistance, you're able to simulate the water line, and you're able to simulate wave formation that offers some amount of resistance to the hull of a ship, and you're able to quantify those resistances as well as drag forces. I've set up 3 examples. One example goes through how long it takes to drain a tank. Another examples that have been popular in the social media realm is the which tank fills first problem. And finally, I have a bottle drop problem that walks you through some of the how the inertial effects translates into sloshing of a liquid inside a container. All right, as I mentioned, the first problem essentially involves a tank that's filled with water. The tank is about 20 inches tall. The water level is about 16 inches. and the diameter of the tank is about 10 inches. Now, through this little orifice at the bottom, I essentially want to figure out, given a time duration, how much of this water level decreases. Now, I'll be laying emphasis on a free surface simulation setup, and I'll also be going through some of the result visualization tools that the software has in order to help you visualize what's happening in the scenario. All right, I'm going to jump into SolidWorks to show you guys a quick setup. Now here I have a tank that's essentially filled with water. Now, prior to running the analysis, it is recommended to create a separate solid body that indicates the height of the water, because during the analysis setup, what we'll be doing is indicating this solid body as a body of water and everything else is air. So you can use the intersect command and essentially create a solid body within this. Now, once you have that done, you can jump into the wizard tool in the SolidWorks Flow Simulation solver in order to set up the analysis. Now, once I select the wizard tool, it's just a 5-step setup in order to set up this analysis. So let's set this up. I'll call the project tank drain. I'll just leave the unit system at defaults. And in the analysis type, this is where there's a slight difference in the 2018 version in that you have the free surface option. Now, with the free surface option, you're actually able to simulate, the air and the water in the same domain. Now, prior to selecting the free surface option, you need to select the time dependent button. So, since this analysis essentially involves the fluid domain varying in time, you have to run this as a transient analysis. Besides that, we have two analysis types, internal and external. Now, we can simulate this as an external analysis and actually watch the water drain out, but that's not going to significantly affect the results that we're seeing here. So in order to simplify the analysis, in order to shorten the runtime, I'm just going to set this up as an internal analysis. Besides, what influences the flow of water is gravity, so I'm going to turn on gravity and ensure that it's in the right direction. And finally, I'm going to select the free surface option. Now, once I have these selected, I can go next. And then within my default fluids interface, I can set up the two fluids that are in my computational domain. So the two fluids here are air and water. Now, since I have the free surface analysis checked, I'm able to create them as an immiscible mixture, and I'm able to simulate multiple fluid phases. Next, the wall conditions typically does not have much of an effect in this analysis, so I'm going to ignore these settings. Now here, you'd want to make sure you set the initial fluid concentration to air, because we will be using this solid body to indicate the body of water. All right. Now, as soon as I hit finish, what happens is the software identifies an empty space and it fills up it creates the computational domain around the empty space. It still looks at this block as a solid body. Now we'll have to actually change that. Now, another item on the tree which you may not have seen before is the initial conditions item. You can use the initial conditions item in order to indicate different fluids on different bodies. So for instance, if I right click the initial conditions item and I select this little solid body that I created and I disable the solid body, it lets me pick what kind of fluid the solid body represents. Now, since the default fluid within the domain is air, now I'm going to select water so that this solid body is disabled, and then the space is essentially filled up with water. Now, as soon as I do that, you should remember to reset the computational domain and include this. A quick and handy way of doing that is if you right-click the computational domain and hit edit definition, you can just switch between 3D and 2D, and the computational domain essentially resets to include the newly added initial condition. Now, once these conditions have been defined, you need to apply boundary conditions in order to cause fluid flow. Obviously, if this tank is completely lidded up and there's nothing really forcing the water to go through, it's not going to change the water level. The water level is going to be stationary. So in order to avoid that, you'll need to add two boundary conditions. One boundary condition within the surface, on the top surface right here, that indicates that this is exposed to the environment. That will essentially drive the fluid flow through the orifice. And you can set that up as an environment pressure, indicating that it's exposed to atmosphere. And then the next boundary condition is essentially at the bottom, where you need to indicate where the water flows out of. So in the same fashion, I'm going to select the inside surface. And I'm going to define that surface as an environmental pressure. Now, once I have both of this defined, now you essentially have an opening where air is actually drawn in, and you have an opening where the water is forced out. So once you set up these conditions, you're actually good to go. Now I'm going to jump into an analysis that I've already set up. And as you can see, I have much of the same conditions that I spoke about during the setup process. I have the environment pressures at the top and the bottom, and I have the water initial condition that indicates, that tells the software where the water is. Now, after I run the analysis, I'm able to visualize through cut plots, what the final level of water is depending on the time moment. So with flow simulation, I'm able to load time moments indicating the level of water at different instances in time. So if I want to see the level of water after 1 second of draining, I can go into the load time moment and essentially the plot updates. Now, another new feature that was added in flow simulation was the transient explorer. So prior to setting up and prior to running the analysis, if you head into the calculation control options, you have an option under the savings tab called transient explorer. Now, as soon as you select the transient explorer, the software loads in a set of parameters to every output in time for you to quickly view those outputs as soon as the analysis is run, so you don't have to create extra animations. So what I've done is I've essentially indicated the mass fraction of water and mass fraction of air in order for the software to give me those outputs as soon as I run the analysis. Now, how do I activate the transient explorer? Once the analysis is run, if you right click the results, there's a transient explorer button that essentially brings up and initializes a little slider bar at the bottom. Now, with this slider bar and the cut plot active, I'm able to play and I'm actually able to see the water level change through the different instances in time. Now you may ask me, hey, this is giving me a qualitative view of the tank drain. What if I want to quantify this? What if I actually want to see the change in the water level? In order to do that, you can take advantage of the XY plot. So the XY plot essentially tracks the change of a parameter on a line. So I've essentially drawn a line from a datum, a sketch line from a datum, and then I've created an XY plot that tracks the mass fraction change along this line. So at 0 seconds, if I actually took a look at the XY plot, it indicates that my water height is at around 410 millimeters or 16 inches. But if I actually move the slider, you can see the XY plot changing the plot as I move the slider, and I can see the water level at different instances in time. So if I move the slider all the way to 3.01 seconds, I'm able to see the final height of the water, which is about about 230 millimeters. So you lost about 230 millimeters, which translates to about 10 inches. So in about 3 seconds, I've lost about 10 inches of water. All right, now this should give you an idea of how the free surface analysis is set up. Now I'd like to jump into the next example, which is the which tank fills first example. So what I did was I essentially took this little snapshot and I created a tank with the same configuration to figure out if water does flow into at a specific flow rate within the first tank, which tank along this line actually fills up first. So this is an interesting free surface problem because it involves the tanks having air at the beginning of the analysis, and then the air gradually being replaced by water. So this makes the perfect free surface analysis. Now jumping back into SolidWorks to show you guys what this looks like. Here it is. This is my little tank. Again, I'm running this as an internal analysis, so I've lidded up most of these tanks. Again, I can run this as an external analysis, but then it might take time to mesh the entire environment, and there's really nothing happening outside of this, and most of the exciting stuff is happening inside of this. So I ran this as an internal analysis as well. Again, setting up the analysis is straightforward. Let's see, I'll call this internal 1. And then you have the unit system, which I leave at defaults. The same procedure as the last time. I can grab the time dependent option. This is primarily going to be an internal analysis. And then I'll set the output times. I can set the total analysis time to about, say 7 or 8 seconds. Now, once I have the total analysis time set up, I'm able to specify the data acquisition frequency like the last time. You can set it up to about 0.1 seconds. Again, turn on gravity and make sure that direction of gravity is, in the downward direction, so that drives the fluid flow. And don't forget to turn on the free surface option. So this setup is much similar to the tank terrain analysis. Now, besides this, I'm actually able to add both the immiscible mixtures like the last time, say air and water. Now, once I have both of these added, I can ignore the wall conditions. I'll just need to make sure the initial fluid within the tank is air, and then I can hit finish. Here, unlike the other analysis, you don't have to create separate solid bodies that indicate the presence of water, because you're just starting off with an empty domain. You can introduce the water through a boundary condition on the top lid. So I've actually created a top lid with a small split surface right here where I'll be applying an inlet boundary condition. So just to show you the setup, I'm going to jump into something that I've already done. And there it is. So you can see I've indicated an inlet velocity at the inlet. Now that split area is going to allow water to flow in at a specific velocity. Now, an important aspect of this setup is to indicate which of the two fluids essentially flow into the tank. So since you have air and water, you'll need to indicate that this is water. Now, since this is an internal analysis, you are forced to create a second boundary condition, because you need two boundary conditions. You need an inlet and an outlet. So you can essentially, pick any of these lid faces and set them as an environmental pressure condition. They usually don't affect the analysis. You could have even split a small surface on any of this just to close the loop with the software. All right. So once the analysis is run, I have some of the outputs set up. And again, I have the transient explorer that quickly shows you through a cut plot how the volume fraction of some of these fluids of water changes as the tank fills up. Now, although I showed you the transient explorer in the last analysis, you can actually visualize in 3 dimensions the fluid flow. Now, in order to visualize the fluid flow in 3 dimensions, you can use a combination of surface plots. So what you can do with the surface plots is essentially take a look at the mass fraction of water on all the faces. Now, when you look at the mass fraction of water, it essentially changes in time, and it gives you, on the surface or on the surface of the tank, what the level of the water is. In addition to this, to visualize the free surface, just to see the sloshing behavior, you can turn on ISO surfaces. And with the ISO surfaces, you can set the value of the ISO surface to 0.5, which will be at the middle of the separation or the middle of the free surface. So as soon as I set this up, you will see a little surface being created on top of this that indicates the separation between the air and the water. Now, as I mentioned, you can use the animation tool within Flow Simulation in order to animate how the water changes, or the position of the water changes with time. The little green diamonds next to the results indicates the results at each instance in time, and the little blue timelines indicates that I'm requesting the surface plot and the ISO surface timeline from the software. Now, once I hit play, you're going to be able to see how, as time progresses, the tanks fill up one after another. Now, with this little animation tool, you need to allow the tank, or you need to allow the simulation to run once over so that all the results are loaded in. And then once the results are loaded in, you're able to get a smooth animation to the end. And there it is. Now you're also able to record this animation by hitting the little record button. And I've actually recorded this and saved it to my presentation. Now with the third analysis, I'm going to be dropping this bottle, and I'm going to be estimating the inertial forces acting on the bottle and how that translates into sloshing of the water. Now, in order to estimate the inertial forces, I can actually take advantage of the motion analysis add-in to see the accelerations. Now, if I can take the gravitational accelerations, or the change in the gravitational accelerations as this bottle is moving, I can translate that from motion to flow and essentially figure out how the water is affected. Now, once I set up the motion analysis, the inputs for flow will be how the gravity direction changes. So now let's say, the gravity makes an angle theta with the vertical of the bottle. Now, as theta changes, the two components, the x and the y component, also changes. And by tracking this change in the x and the y component with the motion analysis tool, I can translate this change into flow and take a look at the water sloshing. So I'm going to show you where you can put these inputs, the g sine theta and the g cos theta input for the vertical and the horizontal directions that influences the fluid flow. All right, for starters, I'll walk you through the motion analysis. Now, in order to run the motion analysis, you'll need to set up, a base, and you'll need to set up the bottle, obviously. The bottle can be floating and the base can be fixed. In the motion analysis setup, we'll be associating a contact between the bottle and the face. You just need to make sure the spatial orientation of the bottle is such that it's in contact with the base. Now, once you've ensured that, you'll need to hit the motion analysis add-in and set up a motion study. The motion study setup is relatively straightforward. All you need to do is do 3 items. Now, in order to set up the motion analysis, I can right-click motion study and say create a new motion study. You'll need to ensure that you do the motion analysis and not the animation or the basic motion. Now, once I have the motion analysis checked, what I'll need to establish contact between the two entities. So in order to assign a contact between the two entities, I can use this little cam follower button. Select the two entities that are about to be in contact and specify the material properties. Here, the material properties don't really matter because this isn't going to do any big friction dynamics or collision dynamics. We're just going to drop the bottle onto this floor. So really, these properties don't matter. Now, once you have that set up, you'll want to adjust the duration of the analysis by moving around this black diamond. Besides that, what's driving the bottle fall are 2 things. The fall of the bottle are 2 things, gravity and an external force. Now, I can add gravity to the study, and then I can indicate the direction to the gravity, which is in the negative y direction. And then finally, I can apply a force to the top of the bottle. Now, by default, if I select a circular edge, the force is oriented along the axis. I can pick any reference within the SolidWorks UI in order to reorient the force. Now, once I've reoriented the force, I can change the force from a constant value to a time-dependent value by hitting step. And here, let's say I'll want a really small amount of force initially, and then I want the force to go away in about 0.1 seconds. So this will apply force for a very short amount of time, and then that'll tip over the bottle. Obviously, I needed to experiment with what force causes the bottle to tip over based on the water level inside the bottle. Now, another thing while running contact analysis is in your motion study properties, you might want to increase the number of frames of calculation, and you also would want to set up precise contact. So anytime you have these kind of smooth curvatures, you'd want to use the precise contact algorithm in order to set up this analysis. And as soon as that's done, I can estimate the motion analysis, and there you go. So it looks like the 0.5 pounds was a little much, but then I actually have a motion study where I believe I've applied a much smaller force. So 0.05 pounds, I've reduced the force to about 10 times, and here is the result. Now, once I have the result from the motion analysis, I'm able to extract the angular displacement through the plots. So I can extract the angular displacement by selecting the results and plots. Now, in the category, I can say displacement. Under subcategory, I can say angular displacement. And for magnitude, I can essentially just see the magnitude here. Now, in order to make a selection for the plot, I'll need to select 3 items. I'll need to select a point on the body that moves. I need to select a point on the stationary body. And then I'll need to select a vertex between these 2 points. So once I have these 3 points selected, I'm able to generate the result, and here it is. So this gives me the change in angle with respect to time. Now I'll need to export this change in angle and essentially estimate the sine and the cos components and how they change. Now I can save all these outputs as a CSV and make those calculations. Now I'm going to quickly jump into Excel to show you the calculation sheet that I have for this purpose. Save file, recent, and here it is. So this is the angular displacement I essentially extracted from the motion analysis. Now I use this angular displacement to estimate the cos and the sine components. Now I multiply the cos and the sine components to check out how the acceleration due to gravity changes with time as the bottle moves. Now, what I need to do is essentially input these values into flow simulation, and then I will have a water sloshing analysis. Now, jumping back into the bottle. Now, the setup of the water sloshing analysis is the same as the tank drain setup. You will have to set up an internal analysis. You'll have to specify an initial condition of water with a solid body defined. Now, the only change in the setup is that if I select the general settings from the input tab and I take a look at my gravity definition, I need to specify gravity as a time dependent component. I can do that by selecting the dependency item, and I can change the dependency from just being constant to F timetable. So this way I'm able to change the value of gravity with time, and this was essentially copy pasted from my Excel sheet that I showed you before. Now if I deleted the last two components, you can see that you have a nice half sign with respect to the Y, and then with respect to the Z, deleting the last two rows should give you a nice little a cosine wave. So this would simulate an equivalent effect of the bottle moving in your domain, and that will simulate the water sloshing. Now again, once the analysis is done, I haven't set up a transient explorer here because the visualization needs to be done with the surface plots and the ISO surface plots. So I'll show both of those plots just to give you an idea of the water level. Oh, the bottle was upside down here. Yep, there it is. And I've set up an animation to show you how the water level changes with time. So we let this animation run once around just so that all the results are loaded. And here you can see with every time step, the surface plot and the ISO surface plot updates to indicate the final level of water along with the final level of the free surface. Yep, I can stop the animation right here and just give you an initial playthrough. There it is. Now with this analysis, you're not restricted to just looking at the qualitative effects of water sloshing. You're also able to quantify this by using surface parameters. So what I've done is I've actually created a surface parameter that tracks the force on the body of the bottle as the water sloshes around, and I've essentially extracted that force as an Excel sheet. Now I'm going to jump into an Excel sheet that shows you how the force changes, how the different components of force changes during the sloshing process. Now, since the primary direction of fall is along the Z direction, the Z component force is the highest, while the Y and the X component, are really low. So this is the kind of information that will then be translated into vibration analysis or basic structural analysis to take a look at the strength of the bottle or the vibration performance of the bottle. Well, just jumping back into the presentation to sum this all up. So let's take a look at the free surface technology summary. As I mentioned, I gave you 3 different analyses. One analysis that goes over tank sloshing or water sloshing. I had water in this bottle. I essentially simulated the bottle falling by running a motion analysis, tracking how the angle of gravity changes, and then translating that gravity change into the flow simulation tool. Besides, I was able to run a really simple which tank fills first analysis by simulating the presence of air inside the tank and then filling it up with water at a specific velocity. You're obviously allowed to change the velocity of the water as the analysis proceeds. And then I obviously started off with a really basic free surface analysis where we look at how the water line changes and how the level of water changes when it's being drained from a tank. Now, I guess unifying theme between all of these is that all of these could have been simulated as an external analysis as well, but then I decided to run it as an internal analysis just to speed up the analysis setup and just to, just so that we only have the results that we need because we're only interested in what's happening within this domain. Now, there's one thing I missed out that I'd like to show you a little preview of, which is the bottle simulation, where the bottle cap is open. So I'm assuming in another analysis that I'm actually simulating the outside air as well. I want to see when the bottle does fall at the given velocity, how does the water slosh outside the bottle. So let me show you a quick result. And there it is. So this was set up as an external analysis, and if I ran this analysis long enough, you can see the water completely drain out due to actually accidentally dropping it. Again, I'm tracking the mass fraction of water and how the mass fraction changes across a cut plot. Another salient feature of this analysis is that I ran this as a 2D analysis. That really speeds up the results and gives me a qualitative view of the results. And then once I'm satisfied with it, I can run a full 3-dimensional analysis. I'll save that for a different webinar, but just know that this can be run as an external analysis as well if you'd like to see how the water behaves when it gets outside the bottle. Now, going back to summarizing the free surface analysis, we have a new wizard button during the setup stage called the free surface button. Of course, once you set up the free surface button, it's almost mandatory to turn on the time dependent and the gravity options. Next, we are able to set up time dependent gravity to simulate the inertial effects on fluid within a tank or a container. And finally, something that I didn't show you was the interface specification. So if you want to simulate a water line, you don't have to simulate a separate body. You can specify the water line just through the initial conditions here. And with that, you can run the little submarine analysis or the ship analysis or the surfboard analyses that require you to specify a water line. Finally, results of visualization. Setting up these analyses are easy, but visualizing the results are key. Now, the Transient Explorer can be used to quickly visualize the results as soon as the analysis is done, so you don't have to wait a whole lot of time for the analysis to load into Flow Simulation. They already come in preloaded for every iteration, and you have a really smooth analysis and you have a really smooth animation at the end of the analysis. You can use this for cut plots, surface plots, isosurfaces, and XY plots. Now, for the results visualization, in order to visualize the free surface in addition to the mass fraction of the water, it's recommended to use a combination of the isosurface plots and the surface plots. Finally, you can use the XY plots to track change in fluid levels, and you can use this in conjunction with the Transient Explorer to get these results quick without having to wait for the analysis to load these results into the software. Well, that's about it. That should conclude this webinar. Again, I hope you found this useful. There are many other enhancements in 2018 simulation. So if you have questions about any of them, please feel free to write to us and we'll be happy to speak to you about them. Again, guys, I hope you found this webinar valuable and I'll take your questions now.